Thank you so much. Thanks for that really nice introduction. And thank you and Kala for thinking of me. It's very exciting. By the way, our department chairs forced us to make those Wikipedia pages. So we all have one. But no, it's a great pleasure to be here. I wish I could be there in person. So yeah, so my background in training is actually in sort of pure control theory. As a graduate student, that's what I did. I didn't really work in neuroscience in any way, but minored in it, had an interest, did a postdoc, 3 years postdocs in neurophysiology, and got really interested in the sort of the intersection between neuromedicine, neurological disorders, and how can sort of people who are trained in dynamical systems and control solve interesting problems in neuromedicine. So I'm going to show you one example of some of the things that we're working on today with regards to epilepsy. And I'll try to be clear, given that you're not asking questions in between. I'll try my best to be clear on every step of the way. Okay, so really high-level introduction. Over 65 million people in the world suffer from epilepsy. So epilepsy causes seizures. Seizures are hyperactivity or hyperelectrical activity phenomena in the brain. It might be a region of the brain, or it could spread throughout where it's just hyperactivation and synchronization. They can last for 10 seconds. They can last for several minutes. A patient may not even notice that they're having a seizure, or they could be on the ground having convulsions. So there's variability in terms of duration and degree of severeness of any particular seizure. You may have been aware of epilepsy, but I'm not so sure everyone's aware of this statistic, which is that over 30% of people who have epilepsy actually don't respond to drugs. Not a single anti-epileptic medication or combination actually suppresses their seizures, and that's 30% of the population. So you might ask, well, what treatments are out there for them? Well, the gold standard is surgery. So the idea here is that within that 30% population, many of them might have what's called focal seizures, or their seizures are starting in a very particular area of the brain. Now, this is a schematic that I showed. EZ stands for epileptogenic zone. This is the seizure focus, the area of the brain that can be triggered to trigger seizures. It's usually not localized in one particular region. It might be a small network of areas in the brain, but focal means that it always starts in that same focal region, and therefore you can actually find it and surgically resect that tissue in hopes of stopping seizures in a patient. So this is an irreversible procedure. Often surgeons will try to take out as much brain as possible without causing morbidities like impairments in speech and vision and motion. So it's this delicate balance of take out as much as you can to make sure the seizures stop, but to try not to impair them post-surgery. Now, even though that's pretty much the gold standard, on average, surgical success rates are 50%. There's actually a variation between 30% success rate to 70% success. What does that mean? That means after surgery, your seizures may return on average 50% in 50% of the patients. And that's just unacceptable. I mean, the reason it's there is because it's actually not trivial to find this epileptogenic zone. So I'm going to take you through the process of how doctors or clinicians do it today in terms of what they call localizing the EZ. And then we'll talk about how we can help them using sort of systems theory. So the first, once a patient is designated as drug resistant and they want to potentially be a surgical candidate, this is what happens. The patient goes into an epilepsy center, a specialized center that treats these types of patients. And the very first thing they do is they go through what's called non-invasive monitoring. They check themselves into the hospital. They stay there for 2 weeks on average. And what happens? Well, all kinds of brain imaging is done on them. They get an MRI scan because the clinicians are looking to see if there's a lesion in the brain or abnormalities that might be triggering seizures, and that might give them a clue as to where the seizures start. Of course, they look at their clinical history. The entire time, they do what's called video EEG. So this is scalp electrodes that are placed on the surface on your scalp, so it's non-invasive, and the patient has the scalp EEG throughout the monitoring phase. They're basically laying down in a hospital room bed for 2 weeks straight while the clinical team is waiting for them to have seizures. And what they do is they look at the scalp EEG data during seizure and say, okay, oh, we see that it's coming from the left hemisphere. We see that it's more temporal frontal area. So the video EEG plus the MRI scans, and then these are other imaging modalities that are used in some of the centers, they try to narrow down where they think seizures are starting. But typically, unless there's a lesion in the MRI, which is about 50% of the time, clinicians don't exactly know where the EEZ is based on this data. They know kind of, okay, it might be left hemisphere or frontal temporal. So in those cases where they're not sure and they can't go straight to surgery, they do what's called invasive phase 2 monitoring. This is when the patient returns back to the hospital, stays for, again, up to 2 weeks, several days to weeks. And this is it's invasive because what the clinicians are going to do is implant electrodes into the brain. Okay, so they have to actually go through a surgery. There's various modalities of how to invasively monitor. One is called electrocorticography, ECOG, where you do a craniotomy. That's where they open the skull and they insert a set of electrodes on the surface of the cortex. That's ECOG here, and they're more macro electrodes. Or they might go through what's called stereotactic EEG. So instead of doing a big craniotomy, they'll just drill small burr holes and they will stick electrodes in each hole, as you see here. And so they're smaller holes, but you can get more electrodes and you can get deep and peripheral coverage. So these are two monitoring techniques that are invasive. The patient recovers from the surgery and they stay in the hospital room for several days to a week because they want a clinical team is just waiting for them to have seizures. Why are they waiting? Because they're going to visually look at the EEG right before each seizure. Here's a little example of a seizure onset. And they look to see which channels are exhibiting some abnormal activity right before the seizure is triggered. And then those channels point to regions in the brain that are suspected to be the epileptogenic zone or the EZ. So they do this for as many seizures as they can capture during the stay. And they form a hypothesis and say, we believe the epileptogenic zone is here, and this is the surgery we're going to perform. And they go and do the surgery. And typically it's a large resection. So that's kind of the process. So it's very lengthy, very detailed, where a lot of data are gathered. Now, one of the things that I mentioned here is they are waiting for seizures. So that's why the patient is in the hospital for several weeks, because the idea is, well, how can I tell you where seizures start without ever observing a seizure? So just want to highlight some of the limitations of here that basically pose the problem we try to solve. Waiting for seizures is problematic. It's high risk for the patient. The patient has their brain often exposed, and there's risk for hemorrhaging and so forth. And it's very, very costly. Every day, it's about $5,000 per day to monitor that patient. A lot of the data are wasted. So if you think of a 2-week stay and a patient has, say, 3 seizures on average that last a few minutes, how much data is actually ignored? Lots and lots of data. And that's when they're not having seizures. But then, of course, the clinicians have no way of inspecting that data at rest and telling anybody where seizures start. It's highly subjective. Actually, interestingly, in the United States, there's no analytical tools that process any of these data to help them find out where seizures start. So it's often prone to human errors. It relies on the expertise of the clinicians. And at the end of the day, they have a lot of uncertainty and large brain regions are resected. And of course, I mentioned that the success rates are still pretty grim. So here's the question I want to pose here. So can we leverage non-seizure data that's currently not being analyzed? So all that information, we have very rich data, electrical activity at the source, all these sources inside the brain with these types of procedures. And they're ignoring much of it because the patient's not seizing. So the question we have is, well, can we actually leverage that data? Can we find this epileptogenic zone when patients are not having a seizure? So Andy, am I allowed to ask the audience a question? Is that without mentioning names? Or am I allowed to?
Absolutely. We can edit it out. No worries.
Okay. So I see that maybe not everybody's a clinician, and you don't have to be a clinician to think about this. But think about an epilepsy patient who might have a seizure frequency of once a week. Okay. So clearly their brain is pathological. So what do you think's happening when they're not having a seizure? So I think of the idea is there's some area of the brain, this epileptogenic zone, that if triggered at the wrong time, will generate a seizure. So what do you think's happening to the EZ when they're not having a seizure? Any ideas? I'm sure many of you are thinking the right thing. What do you think? So think of it like a bomb, a ticking bomb in your brain that goes off every once a week. Why would you not have a seizure all the time? And I can't see anybody's faces. So Andy, if there's any hands, feel free to call on anybody. No answers? Well, so here's our hypothesis, and there's some biological evidence for it. It's because we believe that other brain regions, as a natural protective mechanism, are inhibiting the epileptogenic zone. So there's constant inhibition, trying to clamp down on that epileptogenic zone 24/7. And for whatever reason, maybe it's fatigue, maybe it's a fluke or a specific stimulus that sort of reduces that level of inhibition that allows the seizure to occur, but it's inhibition. And this is our body's way of protecting ourselves from that damage, right? So I want to prevent seizures. So it makes sense to hijack other brain regions to say, now your function is to just inhibit this area. Okay, so we're going to think about that idea and say, okay, if that's the case, then I should be able to, from these data, this intracranial EEG data, I should be able to find two types of brain areas. One area or a group of nodes that are being inhibited, constantly being inhibited in terms of their activity, and another set of areas in the brain or nodes in the brain network that are inhibiting, doing the inhibiting, okay? So we're going to talk about these as sinks and these as sources. And we're going to talk about how we use the data to find that, okay? So just some definitions. So we're going to think of the brain as a network. Nodes are various regions or could be within a region. And edge weights, we're actually going to talk about dynamical influence in a second. But right now, I just like to define what we call a source in the brain network and a sink. So a source is what you might believe is that it's a node is a source if it has high influence on others in the network, okay, on its neighbors, but is not in turn influenced very much itself. So that would be a source. A sink is the exact opposite. It's a node in the network that's getting a lot of influence by other regions, but doesn't really have a strong influence on others. Okay? And so here's what we think is happening. We think that right before somebody has a seizure, the epileptogenic nodes in the network are sources before a seizure occurs. Okay, so they actually trigger and are highly influential to their neighbors in such a manner that allows a propagation of this seizure activity to go through the brain. So the epileptogenic zone are sources before seizures. But at rest, we actually think that the epileptogenic nodes are sinks because they're actually being inhibited. They should be influenced by other regions of the brain that we're going to call sources. So the epileptogenic zone, we believe, has a dynamic role throughout the day, which is when you're not having a seizure, those areas are sink nodes. But right before a seizure occurs, areas become sources to trigger the seizure event. Okay, so most of the time they're sinks, but due to some mechanism, I'm not sure what it is, they lose that influence and they become sources to trigger a seizure. That's our hypothesis. So what we're going to do, we call this the source sink hypothesis. And what we're going to do is from data, we're going to look for top sources and top sinks. Okay. And once we find that from the brain network, from analyzing the intracranial EEG, we are going to now then give the clinicians a hypothetical epileptogenic zone. We're going to say, this is where we think seizures are starting without ever seeing a seizure, okay? And try to leverage that data that they are currently ignoring. Okay, so just briefly before I get into some of the methods, there is biological evidence. I mentioned it's a protective mechanism. So for those of you who are not neuroscientists, it's okay. At a very high level, here's all you need to know. There is what are called neurotransmitters or chemical in the brain. Some are excitatory chemicals, and therefore they cause excitation and activity in the brain. And there's others that are inhibitory, that stop excitation in the brain. There is a neurotransmitter called glutamate, which is an excitatory neurotransmitter. And not surprisingly, it turns out in animal models of epilepsy and in patients with epilepsy, humans with epilepsy, they have too much glutamate in their brain. Okay, so there's evidence that they have extra glutamate, so more excitation. And on top of that, what we find is that there is a protein called a glutamate transporter, okay, that's also in everybody's brains. And its job as a transporter is to remove excessive glutamate in the brain. So we have these regular sort of systems in the brain. We have excitation, we have inhibition. If there's too much excitation, we have these transporters that are removing taking out the excitation and so forth. It turns out epilepsy patients also have too much glutamate transporters. Okay, so this is a sign that at the end of the day, epilepsy patients have elevated levels of glutamate and elevated levels of the glutamate transporters, suggesting that there's this protective inhibitory mechanism around the epileptogenic zone, trying to stop the seizures. Okay, so now to the math a little bit. Okay, so here's what we're going to do. We basically built an EEG analytics tool that's going to process the intracranial resting state data. Okay, resting state meaning they're not having any seizures, they're far away from a seizure, and it's going to produce, at the end of the day, you can think of it as a heat map. It's going to highlight areas of the brain that are red hot, where we believe are the epileptogenic zone, these sinks, and other areas that are not of interest. Okay, so here we go. So to test this hypothesis, we're going to take the intracranial EEG. We're going to build what we call dynamical network models, very simple models I'll go into. From those models, we're going to identify the sources in the sinks, okay, by looking in this sort of 2D plane, and I'm going to define that shortly. And then from those sources and sinks, we're going to now identify what we believe are the epileptogenic zone nodes, the EZ. Okay, so this is sort of the flow of the processing. So let me walk you through each step. So with the intracranial EEG, you get this time series data. Okay, typically you have between 50 to 80 channels. So you have 50 to 80 time series signals going on. We look in a very short window, say 500 milliseconds. And in that 500 millisecond window, we're going to build a really simple LTI model. Okay, we're going to say that if you think of X of T being that vector valued signal, again, in that 500 millisecond window, we're going to build a simple X of T plus 1 equals AX of T, where A is an n by n matrix, n is the number of electrodes. We fit the matrix A just using simple least squares, and we can test to see how well it generates it can simulate the data, and it actually fits the data in very small windows quite well. Okay, so in each 500 millisecond window, I estimated a matrix. Okay, so I get it for the first 500 millisecond window, that gives me a matrix. I slide my window, that gives me another matrix. I slide my window again. So in this way, I'm basically constructing a sequence of LTI models from the time series data. Okay? Now, what do we do with the models? Well, there's variations, but one thing we can do simply is just take an average of the absolute value. So here's where it's a little different. So the A matrix has positive values, negative values, and so forth. What we're interested in here is influence. How much does the activity at time t in a given node influence the future activity in another node at time t plus 1? Okay, and so I don't care whether it's inhibiting, like decreasing the activity, meaning the value in the A matrix is negative, or increasing. I just care about the amount of influence. So what we do when we average this A matrix, we look at the row sum and and the column sum, okay? And then we rank each of the electrodes, which is each row in the matrix, okay, by how large their row sum is, as well as how large their column sum is, okay? And sinks, okay, sink nodes are rows or nodes that have high row values. So what it means is that a lot of the other nodes have great influence on their future activity, but at the same time should have low column values, meaning they don't influence the future activity of their neighbors. So that would come through the column. And so we basically have 2 points. How influential are they? So what is their row sum? What is their column sum? And we plot that as a 2D point in this 2D, what we call source sink space. So rank is not the rank of a matrix. It's the rank. Row rank just means how, if I were to take the row sum of node 3, is it the largest row sum out of all n, or is it the smallest? What is its rank? Okay. And that's what we're plotting in this 2D space. And if you think about this, the sinks, the top sinks in this network are going to be in the bottom right corner, right? They have a high row rank, so they're highly being influenced, but a low column rank. They're not very influential. And the opposite is here. The sources are in the top left, okay? So that's how we go from data. We build these LTI models, and we look at overall average influence, and we plot in this 2D space, and we get our sources and sinks, okay? And then what we're going to do is just quantify some metrics. We want to be able to say how much is a particular channel, which is a dot here, a node in the network, an EEG channel. How much of a sink is it, and is it being influenced by top sources? So the ideal sink is down here, ideal source is up there. And so we can compute what we call a sink index, which is literally just the Euclidean distance from the ideal sink, okay? We can also compute, so that's the sink index, is how far are you from basically the ideal sink. The largest, the maximum being square root of 2. We also then compute what's called a source influence for that node. How much is that node also being influenced by the top sources? Because remember, our source sink hypothesis said that there's a group of regions, the top sources, that are constantly inhibiting the sinks. So we need to know that these are not just sinks, but they're being influenced by the top sources. So you can also compute what's called a source index to say how much of a source is a node. And then from that, we can compute the influence. So if I'm node I here, I have a certain sink index, but I also can compute the source influence by taking this weighted sum, AIJ, multiplied by how much of a source that is. So if you're influenced by the top sources as shown in this diagram, then the source influence of these nodes will be high because they're sources. And if they are influencing the node, that will come in as a high weight here in the AIJ. Okay. And then we also believe that the epileptogenic zone is a coordinated group of nodes to be able to trigger a phenomena like a seizure. So we look for connections, connectivity within the sinks. We call that metric connectivity of I, okay? And then what we're going to do is just take the product of the 3 metrics and create what we call a source sink index for each node in the network. So a source sink, and our hypothesis is that the source sink index will be high if you're epileptogenic and low if you're not. So it could be converted into a heat map picture like this, so as an example. Okay, I hope that was clear. And now I'm just going to show you a couple of examples and then wrap up here to see how we did. So we tested this idea on a preliminary data set of 31 patients who went through stereo EEG. So those are the burr holes drilled. And in this data set, roughly equal gender, we had 14 successful outcomes, 17 failed outcomes. So let me just show you what some examples look like, and then I'll summarize the whole data when we applied this source sink tool to it. So here's an example of a patient, and I'll walk through each panel here, of a successful surgical outcome, okay? That means the clinicians identify the epileptogenic zone. That's written in the table down here. Clinical EZ says these channels, which are labeled by a letter and a number, L bar 2 to 4, that's shown here in the top right implant. the actual ones that are red, it starts from the deep areas, number 1, 2, 3, 4, all the way up to about 10 to 16 contacts per electrode. This is the area that the clinicians treated, okay? And they got it, and this person had a successful surgery. When you look at what the source sync did and you say, okay, what we did is we took 5 minutes of data at rest when they're not having seizures. We built our models. We computed the 2D source sync maps, as you see here. These are the top sources. We are drawing arrows to which nodes they're influencing the most, and they happen to be influencing many of these syncs down here. Let me zoom in a little bit on that. And you might be able to see that we color coded the channels in red that the clinicians identified through their normal process as epileptogenic. And as you can see here, we have really strong agreement between our top syncs. In fact, this is the perfect example, right? We have perfect agreement. Our top 3 syncs are exactly the 3 nodes that the surgeons treated, the clinicians treated. They are syncs. They're being heavily influenced by the top sources, and they are highly connected to the other syncs. So exactly meeting all of our criteria. And we can compute their index. And in fact, what you see is the source sync index here overlaid. So here's a case where our analysis at rest completely matches the clinicians whose analysis is predominantly looking at seizures, okay? Completely different data set, but we're converging to the same answer. So this was a nice example. The one thing I wanted to point out is what you can do with this methodology. You don't have to just have a static heat map answer. As you remember, as you have this time series over time, we can compute an A matrix for each, we compute an A matrix for each 500 millisecond window. You can actually compute the source sync index from every A matrix. So what we're showing here for this same patient is what the source sync index looks like as you move through time. And what's interesting about here is this is when they're completely not having seizures. This is a sync index, sorry, just how much of a sync are you? Some of these top 3, these arrows are pointing to where the clinicians believed were the epileptogenic zone. And what I want to just point out from this heat map is this is telling me how much any channel is a sync. And so these are the top syncs at rest. Interestingly, 6 minutes before a seizure, a few of those syncs turn into sources. They become blue, which means there are more sources. And if you look at that, which ones are turning blue? Exactly the ones that the clinicians, the 3 here, are exactly what the clinicians treated. There's one down here, the neighbor, L5, is also blue. So that means they turn into sources, the seizure gets triggered. And then through natural mechanisms, they're trying to be inhibited by the rest of the brain. So they go back to being syncs. So you can view this phenomenon by looking at how they migrate from that source sync figure. When you go at rest, the epileptogenic areas, the clinical EZ are the red dots, they're syncs. And then right before a seizure, you watch how they migrate to become sources. A seizure triggers, the rest of the brain kicks in and tries to inhibit again, and they go back to syncs. Interestingly, there's some very bouncing back of sources and syncs right after the seizure, but then they return right back to syncs during rest. I'm going to highlight one more example here of failure. This is a case where the clinicians treated this area. Let's see, are the contacts listed here? Yes, I think some of these areas that are shown here. Okay, so the red areas are where the clinicians treated. I think you can see my cursor here on the top right panel, the implant. And this person failed. In fact, when we looked at the data at rest, we had no overlap between what we thought source syncs nodes and what the clinicians treated. We actually saw all the syncs being these M channels, M over here. Okay, so a completely different area of the brain. This patient actually returned, had a new invasive monitoring procedure, and the clinicians later identified the M bars, the same location as we found from the first data set. They later resected that, and this patient became seizure-free. So this is a really nice example where we disagreed with the clinician, and the clinicians came back, were able to actually, on their own, independent of this tool, determine a region to resect that matched what we said. So this was a really nice sort of example where we have, they can test out our hypothesis, although they didn't see any of our data for this is all retrospective. And just more, this is another failure where the top sources are not pointing to the top sinks. This is an interesting case and the sinks are not the epileptogenic area. So there's mismatch between what the clinicians resected and what we saw were the top areas or the epileptogenic regions based on resting data. And this was a failed outcome. Okay. And then finally, I'm going to end here. So that's just a couple of examples. We did this on 31 patients. So what we wanted to do is we wanted to demonstrate whether the source sink index carries predictive, has any predictive value. Meaning, if I were to look at the source sink indices, can I predict the surgical outcome of the patient through a retrospective analysis? So what we did is we built a logistic regression. So we're building a model on the probability that a patient will have a successful surgery as a function of various features, X1, X2, X3. And these features are exactly our indices that I mentioned before: sink index, source influence, and sink connectivity. But what we're actually putting into these features for the logistic regression is the difference. So for example, X1 carries the information of how much of a sink is a particular channel. But remember, PS is the probability of success of a patient. So what we're going to do to compute this feature X1, we're going to take all the clinically annotated nodes and average their source sink indices, okay? And from that mean, subtract the average source sink indices or sink indices from all the rest of the channels, okay? So we're basically taking the clinical annotations and looking at their sourcing indices and taking the difference from that average from everybody, all the other channels. And the hypothesis is that if the clinicians got it right, then the clinical annotations where the brain regions they treated should have high source sink indices in their EZ nodes and low source sink indices everywhere else. So this would be a very positive number for successes. Otherwise, it would be a low number. And so when we tested that out by basically computing these source sink features for each patient, we were able to basically predict outcomes. So you build a logistic regression, you train these coefficients. We just are using all the data. Well, actually, no, she does split the data and training test set. And this is an ROC curve on training data. And what we're plotting here on the right is the probability of success, the model, as a function of the source sink index features here. And we're showing what that probability looks like for all the patients who had successful outcomes and all the patients who had failed outcomes. And you can see that the majority of success cases have a higher probability of success based on our model, and the failures in general have a lower probability. Of course, there are outliers, but this is something that I think was amazing in the sense, I mean, we had a lot of support from the clinicians in helping us with this particular idea. It's definitely a team effort, but what's sort of phenomenal about this is we are using 5 minutes of data that they don't even look at. We're building these models, these network models, and we are testing a hypothesis based on biological evidence. And we're able to predict with reasonably high accuracy when in that particular retrospective set, their surgical success rate was 45%. And we were able to predict this. So what's interesting is we're able to predict these failures. So had they seen the outputs of the tool before they did the surgery, maybe they would have gone back and looked again to say, why is the tool disagreeing with us? So I just want to stop there because I want to try to, hopefully I have some room for questions. Want to acknowledge the main players of the team here. So this work is the thesis work of Christine Gunnadóttir. She's from Iceland and she's in her 5th year PhD, and this is all her work. She's an amazing student working with 5 different epilepsy centers now to test her hypothesis on over 70 patients is what we have today. And the neurosurgeon here, Jorge Gonzalez Martinez, he used to be at the Cleveland Clinic, which is the largest epilepsy center in the world. He does all those implants, but he just recently moved to University of Pittsburgh Medical Center. And it was the 3 of us that over a year ago were stumped by some of the data and some of what the models were saying, and saying why we were stumped because we were processing the data. She had this idea of sinks, and we were seeing the epileptogenic zone as sinks. And we're saying, why is that the case? They should be sources. And then we started digging deeper and saying, of course, they're sinks, because if you're at rest, they should be inhibited. They should be influenced by other brain regions. And it came out, that hypothesis emerged from the three of us, really, really struggling with the data that we have. Okay, so I'll pause there and happy to take any questions.